Welcome to Meteorology Matters. Today we're looking at something really quite strange, a real climate puzzle. Imagine this. A huge part of the Atlantic Ocean is
Yeah.
cold. And it's actually getting colder, even while the planet overall is hitting record high temperatures.
It does sound completely counterintuitive, doesn't it? Like finding an ice cube floating in a hot bath.
Exactly. And understanding this cold spot is, well, it turns out it's pretty key to understanding the bigger climate picture. So in this Meteorology Matters podcast, we're going to explore these surprising connections. Why is this happening? What does it mean for our weather? And really, why should you care about it?
That's a great topic. Because, for years, this was a genuine scientific head-scratcher, a real anomaly. But recent work, some really intensive research has started to piece it together. This cold blob, as people call it, it's a specific spot in the subpolar Atlantic south of Greenland. And measurements show it's cooled maybe by up to 0.3 degrees Celsius over the last century or so, while everywhere else is warming up.
Right, 0.3 Celsius, or about half a degree Fahrenheit. That's not tiny, especially when the waters right next to it are warming. And like you said, there was this debate for a while, wasn't there? Was it just ocean circulation doing this, or was the atmosphere somehow involved too?
Well, the latest thinking, the newest research, points pretty clearly to both. It seems ocean and atmospheric processes are pretty much equally responsible.
Okay, both.
And understanding that mix is vital because this isn't just some local quirk. This cold patch can actually disrupt things like the jet stream, and that affects storm tracks, big time.
Okay, so let's break that down. The ocean part.
Yeah,
That involves the AMOC, right? The Atlantic Meridional Overturning Circulation.
that's the one, the AMOC. It's this absolutely enormous system of ocean currents.
Like a giant conveyor belt moving water around the Atlantic.
Precisely. It brings warm, salty water up from the tropics towards the north.
Where it cools down.
It cools, gets denser because it's salty and cold, and then it sinks deep down. And then it flows back south again, deep underwater.
And this whole circulation, this conveyor belt, is massively important for climate, especially here in Europe and North America.
Hugely important. It helps regulate temperatures, distributes heat. It's a major climate driver. And the origin of this cold blob, it's directly linked to a slowdown in the AMOC.
Ah, okay. So why is it slowing down?
The main culprit seems to be freshwater. Lots of it. Melting ice from Greenland, mostly. This fresh water pours into the North Atlantic and it dilutes the salty ocean water.
Making it less salty and less dense.
Exactly. Less dense water doesn't sink as readily. So that sinking part of the conveyor belt, the engine driving it, it weakens. The whole system slows down.
And less heat gets transported north,
Yeah.
leading to that cooling south of Greenland.
That's the mechanism.
Yeah.
And we have data going back, over 100 years showing this long-term weakening trend in the AMOC. Plus, the climate models really back this up. Only the models that simulate a weaker AMOC can actually reproduce the cooling and the freshening, the lower salinity that we've observed in that specific region.
Okay, so that covers the ocean side. But you said the atmosphere is equally involved. How does a colder ocean surface affect the air above it? Is it just like locally cooler air?
It's more than just cooling the air directly. It's about moisture. Colder water means less evaporation.
Right, less water turning into vapor.
And less water vapor in the atmosphere means, well, water vapor is a greenhouse gas, isn't it? It traps heat.
Ah, I see. So less water vapor means less trapped heat locally.
Precisely. You get a drier, cooler atmosphere right above that cold patch. And this drier, cooler air then feeds back onto the ocean, helping to keep it cool, maybe even making it a bit cooler still.
So it's feedback loop. The cold ocean makes the air cooler and drier, which then helps keep the ocean cold.
Exactly. It amplifies and sort of locks in the cold. But it's like turning down the local greenhouse effect just in that area. It really shows just how tightly interwoven the ocean and atmosphere are. It's such a delicate balance.
Okay, so bringing this back, why should someone listening right now, maybe miles away from the Atlantic, why should they be concerned about this cold blob? What are the real-world impacts?
Well, they're quite significant, potentially. First, as I mentioned, messing with the AMOC and creating this cold spot disrupts the jet stream. That directly influences weather patterns, where storms go, how much rain falls across North America and Europe. Think extreme weather events.
Okay, so more unpredictable weather.
Potentially, yes.
Sure.
And then, if the AMOC were to weaken drastically, or, in a worst-case scenario, collapse, that could trigger a really sharp temperature drop, especially across northern Europe. We're talking major changes.
Wow, okay. What else?
There's sea level rise. Changes to the AMOC can actually affect sea level heights, potentially making sea level rise worse along the U.S. East Coast.
Really? How does that work?
It's complex. related to ocean dynamics and how the currents pile up water. But a weaker AMOC can allow coastal sea levels to rise more on the western side of the Atlantic. And of course, changing water temperature and salinity has huge impacts on marine life. Fish stocks, ecosystems, they're all sensitive to these shifts.
So understanding all this helps predict future climate changes better, especially for places like Europe.
Definitely. Improving our climate models with this understanding is crucial for forecasting, especially regionally.
Just when it sounds like we're heading towards a potentially concerning slowdown, there's this other twist, right? Something about a possible backup system in the Arctic.
Ah, yes. That's a really interesting, fairly recent line of research. The idea of some resilience in the system.
So what's happening there?
Researchers are observing something called Atlantification in the Arctic Ocean.
Atlantification, meaning it's becoming more like the Atlantic.
In a way, yes. The Arctic is generally becoming warmer, less ice-covered.
Yeah.
And warmer, saltier Atlantic water is pushing further and further into the Arctic Ocean each year.
Where is this happening most?
We see it strongly in places like the Barents Sea. That's actually expected to be the first part of the Arctic to become ice-free year-round, and also north of Svalbard.
Okay, so the Arctic is getting more Atlantic-like. How does that help the AMC, which relies on cold, dense water sinking way further south?
Well, the twist is, as this warmer Atlantic water interacts with the Arctic conditions, and particularly as sea ice forms in winter, the remaining water becomes saltier and denser. And it turns out the Arctic, through this Atlantification process, might actually be starting to produce more dense water than it used to.
Oh, interesting. So it's creating dense water in a new place.
Kind of. It seems to be partly compensating for the slowdown in dense water formation in the traditional areas, like the Greenland and Norwegian seas.
So like a backup generator kicking in?
That's one way to think about it. It suggests the system might have more resilience than we thought. But, and it's a big but, we need more research, there are still questions about whether the dense water formed in the Arctic is quite dense enough, or if it can effectively replace the really deep, dense water formation that historically happened in the Nordic seas and powered the strongest AMO circulation.
So maybe some resilience, but the jury's still out on how much.
Precisely. It's an active area of study.
So wrapping this up, it's clear this seemingly simple cold spot in the Atlantic is tied into these huge, complex planetary systems, ocean currents, the atmosphere, melting ice. It's a really powerful reminder of how interconnected and, frankly, how delicately balanced Earth's climate really is.
Absolutely.
And our understanding is clearly still evolving, which hopefully helps us anticipate what's coming. It really makes you wonder, doesn't it? What else are we going to discover that shifts our perspective on how all this works?
That's the fascinating part. This research really drives home that even with global warming as the big picture, these regional variations, these anomalies like the cold blob, offer vital clues. They show us the nuances, the intricate ways the planet responds. It really underscores, I think, why we need to keep digging, keep asking questions, and be open to complex answers in this changing world.
Indeed. Well, this Meteorology Matters podcast is a collaboration with meteorologist Rob Jones. You can follow Rob's work. He's on Instagram at meteorologist. That's METEOROLOGIST. On TikTok, look for TV Meteorologist. And over on YouTube, search for Rob Jones Hurricane. That's Rob Jones Hurricane, all one word. And you'll also find the Meteorology Matters podcast playlist there. Thank you so much for joining us today as we explored this piece of the Earth's amazing, intricate climate puzzle.